Okay, so lesson 30, graph of tangent theta and graph of reciprocal functions. Basically, sine, cosine, tangent. Remembering how to do those. Their reciprocals, and then just any type of reciprocals in general. So, basic review. I don't know how much we need this, but doesn't hurt to mention it, right? So remember sine x, the graph of y equals sine x, has a period of 0 to 2 pi, right? So a period of 2 pi. Has a range of -1 to 1, right? And it's always centered on the x-axis unless we shift it up or down. Sine starts at 0, goes up to a max, cuts through the axis, down to a minimum, cuts through the axis again, right? The difference with cosine? Cosine is basically the same graph, except it is shifted, right? So basically, if you take your sine graph and you shift it left pi over 2, you have your cosine graph. Okay? Same period of pi, -1 to 1, same type of similarities, right? And we practiced a lot last year with kind of cutting the graphs into quarters, except that a quarter of 2 pi is pi over 2. Okay. Tangent. If I had to guess which graph you're not going to remember of sine, cosine, and tangent, it's probably going to be tangent, would be my guess.
Is it tangent just like the word lines? It's like almost just like a new function. But it's like there's a bunch of them. They're like asymptotes.
Yeah, I remember those.
I think of tangent as a whole bunch of like the cubic graphs, basically, is what I think of them. The key is remembering, I mean, if you know tangent, then you can figure out cotangent. But it's just remembering where the zeros are. So in other words, where we cut through the x-axis, as opposed to where the the vertical asymptotes are. You know, it's just remembering all of that. Now, one thing I will remind you of, tangent. I should have asked. Tangent is what over what in terms of tangent is sine x over cosine x. And here's how that helps me. Sine is in the numerator. So when sine equals 0, when there's 0 on top of a fraction, that fraction is 0. So the point I'm making here is that your zeros, you know what I mean when I say zeros, right? Those x-intercepts of sine are going to have the same x-intercepts of tangent. When cosine is 0, what about 0 in a denominator? It doesn't exist, and so those are our vertical asymptotes. And so when cosine equals 0, so if you think about your cosine graph, those are your vertical asymptotes. So that's kind of a way, you know, if your calculator lists on a certain question and you're trying to visualize your tangent, those are some connections you can make if you can't quite remember where it goes. So, I'm going to go ahead and label this. We have pi over 2. I normally label it the same as up above, but that works a little differently when I scooted my page up and I can't see it. Okay, so I labeled pi over 2, pi, 3 pi over 2, and 2 pi. In my notes, just like up above, I have -1 and +1 labeled. Although I'll be honest, in tangent, we don't really do a whole lot with the -1 and 1. Okay, so where are my zeros here for tangent?
Pi, 0, pi, 2 pi.
Okay, so my zeros happen at 0, pi, and 2 pi, because those are the places that sine touches the x-axis. And where are my asymptotes?
Pi over 2, 3 pi over 2.
Yeah, pi over 2, 3 pi over 2. Do me a favor and please draw all those in. Don't make me assume that they're there. Okay, draw those in. And then other than that, tangent is an increasing curve. So it looks like y equals x cubed. So don't forget your arrows on top and bottom. because this does extend indefinitely either direction. Looks something like that. Coming back to you? Graphs, these type of graphs in general, or tangent graphs?
Tangent, but I loved this entire unit last year.
Okay. Only if everyone did.
It was different.
I would say it was a different experience. I mean, you know.
I mean, and it was weird to kind of like have homework that was just different. Like it wasn't like, oh, take your book and do this, like
Yeah.
papers over it.
Yeah. And I do worksheets. I think I do worksheets in that section just because otherwise everyone's setting up their graphs differently. And that makes the grade 10 times harder. You know, you've got some people that are going to take up the whole width of the page. I've got some people that are going to shrink it down, make it tiny, and then this way at least I have something in common as I grade them. So, okay. So, graphs of reciprocal functions. So, when we talk about sine, what do you know about sine? Sine pairs up with cosecant, right? We usually talk about those being inverse graphs, okay, inverse functions. So in order to graph sine, or excuse me, in order to graph cosecant, it says to use sine. And if you recall, sine of x is equal to 1 over cosecant x, right? Or, I don't know, maybe I guess for this one, if you prefer, cosecant x is 1 over sine x. Whichever, I guess the other one makes sense there. Because if we talk about cosecant x being 1 over sine, notice sine is in the denominator. Any place sine equals 0, what's that going to be in cosecant? It's going to be an asymptote, right? So if you remember when we drew these, I always kind of had you guys draw the sine as just kind of a dotted line. My asymptotes happen at the zeros. So wherever sine has a 0, that's an asymptote. And then what do you remember doing? Yeah. Flipping the parabolas upside down pretty much. Okay. So we'll talk when we get to, I'll probably save it for example 5. When we get over to that last page, we'll kind of talk about exactly the how and why that works. Kind of some, rules there. But, for what we talked about last year, it was just kind of these parabolas flip, reflect. I guess I can kind of draw on there. I'm glad you guys know what that graph is supposed to look like. I did not allow for that. I just thought, less times I have to move the screen. Okay. We will, I guess, and I'll go ahead and mention it. We will talk about when we get to the final examples and we're drawing some inverses that we aren't familiar with. I'll kind of go through some key points. And we've already talked about the fact that a 0 here becomes a vertical asymptote, right? We've already talked about that one. One of the other points I'm going to talk about is that points where y equals 1 or y equals -1 will stay the same. So notice, when y equals 1, what happens? That's the same point, isn't it? I know I remember making the point last year that the parabolas touch each other, don't they? Okay, and when y equals -1 down here, the points touch each other. And then the other key point we'll talk about is the fact that the large positive values will instead become small positive values. The small positive values will become large, so they kind of flip places. So the idea is that, like this right here, once we go past 0, 0, these are very small positive values, right? Well, now, in the inverse, the equivalent x value up here is a very large positive value. Okay? And so those will be some of the keys that we will use. Now, in all honesty, you guys just probably kind of remembered what cosecant looks like. So, okay. Page 2. we got to practice our secant and cotangent graphs. So notice on the first one, use the graphs of cosine and tangent to sketch the graphs of secant and cotangent. So what do we know that's going to be important here? Cosine is the reciprocal of secant, and so we know that secant x can be written as cosine x, 1 over cosine x. And that just reminds us, if cosine x is in the denominator, then it can't equal 0. So any place cosine normally equals 0, those are asymptotes. And thus, what I taught you last year. Zeros become asymptotes. And then, as we do this, same thing about flipping the parabolas, right? Now, with cosecant, I always said, okay, draw me 2 full parabolas. With secant, I said, we usually talked about it being 1 and 2 half parabolas, right? Which I know, if you're going to get mathematical, that's still 2 full parabolas, but that was kind of your minimum expectation there. All the same things I talked about earlier are still there. Okay. Now, I don't know, did we ever graph tangent and cotangent on the same graph? That's not really how I teach it in pre-cal. It really isn't. So, So, as we look at tangent, well, first of all, we're trying to graph cotangent, right? So, one thing to think about is cotangent x is the reciprocal of tangent x, right? So cotangent is 1 over tangent. You could also, what else do we know about cotangent? You could also think about it as cosine x over sine x. So we can either think when tangent equals 0 or when sine equals 0. Those now become asymptotes, right? And then when cosine equals 0, those are your zeros. What ends up happening with tangent to cotangent, I think of it, I think of the asymptotes and zeros just kind of flipping places. I don't try to remember how, I think I just taught it as more of a memorization. I know. I taught it as tangent, you start with a 0 on 0. With cotangent, you start with an asymptote. That's how I taught it, isn't it? So, anyways, these zeros are going to switch and become asymptotes. And then what about those asymptotes? They're going to become our zeros now. And then the other thing that needs to change?
Do they start in the top left?
Yeah. Instead of being increasing pieces of functions, they are decreasing pieces. Okay? That graph is just a big old mess, but maybe part of the reason I don't know, I've never really thought about why I do that pre-cal level, but maybe part of the reason I teach tangent and cotangent is just 2 separate things. So, and do remember here, the period instead of being 2 pi is a period of pi. I did forget to mention that. So, and you can notice the same thing that what we talked about earlier. Zeros and vertical asymptotes, they trade places, right? Points where y equals 1 or y equals -1 stay the same. Well, guess what? Where my tangent and cotangent graphs are crossing is supposedly where y equals 1. Okay? And then the idea that, so like a small positive value here is now a large positive value. Okay? Large positive value here is now a small positive value. So they kind of flip-flop places there. Same is true in the negatives. Okay? Okay, that's review, right? Let's see. I do have to move my screen up. Oh, that's weird. It's behind it. Did you guys see that?
Yeah.
I didn't realize that that's where the writing went when I scooted it. Interesting. Sorry. Easily amused here. I mean, I walked in the other day after school, and Natalie had the Apple TV going on here. She was watching a show from probably Netflix, and she also had the whiteboard going. Like, she could draw on her show. And I'm like, I didn't know you could, bring the whiteboard up and draw on your show. Like, I don't know. I was just kind of like, you can do that? Yeah. Okay. So, cosecant of theta plus 45. What do we know?
Is it a cosecant graph that is moved one direction, specifically to the left?
I would say, depends on what this one direction is, but yes. Okay, so if it's theta plus 45, it's in the parentheses. We're going to go opposite, left to right, opposite the direction of the sign. So this is going to be I'm going to bring it up. Speaking of whiteboard, forgot to turn the whiteboard back on, which means I have to erase all of this stuff. Okay, try again. Okay, so there we go, that's better. So plus 45 is going to be left 45 degrees. I know you guys often like to think degrees, but honestly in this particular problem, I prefer radians just because I struggle to think radians on a sine or cosine graph. So this is also going to be the same as thinking left pi over 4. And then the other piece of information to remember is that cosecant is the reciprocal of sine. Okay, so set it up. I personally am going to pretty much set up my whole line as 2 pi. If you recall, I then kind of like to just eyeball it and split it in half. And then I'll split it in half again. So I have pi over 2, pi, 3 pi over 2, and 2 pi. Based on the fact I'm going to have to move left, I'm going to go ahead and put a negative pi over 2 to the left. Now, if you want, you could go ahead and trace in sine, couldn't you? Oh, I forgot to put in 1 and negative 1, didn't I? So you could trace in sine real lightly. I wish I had a light gray. I don't have a light gray, I just have a dark gray. What happens if I trace in yellow? Right? Does that work for you guys? Okay. So that's my normal sine graph. I guess I didn't ask you, I just did it. Sorry. Now what?
Well, we know that there's going to be the phase shift to the left.
Yeah. Yeah. I went with the basics to get us started, and maybe you guys went ahead and put more tick marks in, but we don't have pi over 4s up here, do we? We only have half pi's. We don't have quarter pi's. So whether you label them or whether you just put them in, you've got to have the halfway marks of what we already have, don't you? Okay, so this would be pi over 4. That's 2 pi over 4 already. So there's 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4. Ooh, that's not readable.
Can I just do the tick mark?
You can. Okay, maybe regretting. Maybe I should have just done the tick marks. Because that's getting to be a lot, isn't it? But okay. What am I doing with this original sine graph? It's going to shift, right? So each of my zeros now is going to shift negative pi over 4, which is equivalent to a tick mark, right? So if I shift that, we're going to start at negative pi over 4, cross at 3 pi over 4, and end at 7 pi over 4. And I don't know, I sometimes need my highs and lows put in. I'm going to max at pi over 4 and a min at 5 pi over 4. Okay, so I'm using the red as my main graph. What do we need to go with the zeros? Asymptotes. So asymptote at negative pi over 4, 3 pi over 4, and 7 pi over 4. And then you can flip your parabolas, right? Okay. What do we know about example 4?
It's a secant graph translated 20 degrees to the right.
Okay. It's secant graph. And we know a secant is 1 over cosine. And this minus 20 says that we're going to go right 20 degrees. And the unfortunate part is that's not a nice, neat radian that we know, is it? Not that you couldn't change it to radians, but in this case, I think changing it to radians would make it worse, personally. I'd rather have to fight the degrees. So, what do we know about degrees? Instead of 2 pi, I'm going to label this 360, right? In the middle of 360 is 180, and I've got my 90, and 270. So 90, 180, 270, 360. And where are we going? To the right 20 degrees. Sounds like tons of fun, doesn't it? So right 20 degrees. I mean, you could go in and label these all by 10 degrees or something fancy like that. Or here's what I'm going to do. Okay, so between 0 and 90, where is 20? I'm going to say 20 is approximately here. Does that seem good? Okay. What's another marking I'm going to need to know? Past 90, I probably should put in a 110. Past 180, I should probably put in a 200, a 290. I guess if we're going right, I'll put in a 380. However you want to make that happen. Okay. What basic graph am I graphing here? Cosine. So if I'm graphing cosine, normally, oh, I didn't put my -1 and 1 in there, did I? I am guilty of that. So, you know, like I will remember later, but okay, so normally we'd start above 1, or at 0, 1. Now I'm going to start above 20. I want to cross through 110. I'm going to have a minimum under 200. Cross through 290. And have a max over 380. Something like that. line is not ideal by any means. Okay. Asymptotes at your zeros. So asymptotes at 110 and 290. And then flip your parabolas, right? Okay. It's a lot of old news. It's not that we do a ton with these graphs, but you just need to be familiar, able to handle these. Okay. One last page. We're going to sketch the reciprocal function of these functions shown below. The key is we don't necessarily know what we're sketching here, do we? Okay. Now, I kind of mentioned some key points earlier. And so we're going to think about these key points. Okay, I've got 3 of them. I've already mentioned them all. First of all, what did I say about zeros and vertical asymptotes? Zeros and vertical asymptotes are going to trade places, right? If it was a 0, it becomes a vertical asymptote. If it was a vertical asymptote, it becomes a 0. So as we look at this graph right here, we'll go step by step. We just have the graph of a line, yes? How does this first point affect this?
There's an asymptote too.
Okay, it was a 0 here, so now I'm going to turn this into an asymptote. Got it? Okay, key point number 2. Points where y equals 1 or negative 1 stay. So points where y equals 1 or y equals negative 1 stay. So, it's kind of an eyeball game here, because we don't exactly have ordered pairs, do we? But what I tend to do on this one is I try and, well, there's one that's not an eyeball. It's pretty obvious. This point here that's at 0, negative 1, I'm going to put a dot, because that's going to be a point on my new graph. And then, I don't know, maybe between 3 and 4, almost 4, somewhere there. My guess is it's actually supposed to be above 4 if you go with what the slope is there. Probably supposed to be 4, 1. But those 2 points are going to be part of my new graph. So I'm going to make sure my new graph crosses through those. Okay? And 3, the one that probably hasn't made the most sense yet, but... Okay, so large positive values will become small positive values. Small positive values will become large positive values. And as I mentioned earlier, the same is true for negatives. Large negative values become small negative values. Small negative values become large negative values. Okay? So those are the 3 key points. Now, how this last one affects. It's so hard for me to think about this, but okay. So as we look left here, this line is going infinitely down, yes? It's getting farther and farther away from the axis. These are technically very small negative values, right? So where are large negative values? Closer to 0. So what's going to end up happening is this is going to end up as a horizontal asymptote. And you're going to be running along the axis, because gradually what needs to happen? If these are getting farther away from the axis, right, as we were to go this way, our graph would need to get closer. And so, and realize we have to cross through here. So the idea here is it's going to run along an asymptote. And it has to cross through that point because that's where y equals -1, yes? Now, first of all, we see a vertical asymptote, yes? You know what your graph does at a vertical asymptote, don't you? It's going to go infinitely down or infinitely up, depending on the situation. Well, we have no reason to cross above, so this one's going to go infinitely down. But also keep in mind, these values as you get to the right of the x-axis, they're getting closer and closer to the y-axis. So our values need to get farther away. So it's going to look something like that. And we kind of reverse the process on the other side. We can also use the fact, didn't I just teach what happens at a vertical asymptote? Well, usually one part's down, one part's up. Now, we can't see the equation, so we don't have an equation here to know. But that's usually what happens. But here's the other thing. This part of the graph is positive. So where's my reciprocal graph have to be? Up there, positive. After we get past this asymptote, this point is very close to 0. So I need a point that is very large, very far from 0. We're going to go down. We're going to cut through this 0, and we're going to be on top of that horizontal asymptote.
Where does the horizontal asymptote come from?
Say what?
Where does the horizontal asymptote come from?
We don't really know there's a horizontal, it's the fact that when we talk about a reciprocal graph like this portion of the graph is below the x-axis. So our portion of the graph needs to stay below the x-axis. If this is going infinitely smaller, this is getting closer and closer to 0. Because it can't cross over and become positive if we're already negative here. There's nothing that tells us that is a horizontal asymptote, but that's what it's acting as. Now, think about this. This is a line, yes? Without any bells and whistles, well, what equation of the line is this? Okay, maybe more than I want to get into. This is an equation of a line, yes? General equation for a line is y equals x, if you will. This one just isn't exactly y equals x. What would be the reciprocal of x? 1 over x. Does this graph look like 1 over x? This is the reciprocal function graph. You know, that one we learned over a year ago at this point? That's what we're looking at there. Okay. One last example. The graph of f is shown. Sketch the graph of the reciprocal function. This is just going through the steps. So I'm going to go point by point. Zeros become asymptotes, asymptotes become zeros. So let's start with easy. I see a 0 at -3, so that's going to be as an asymptote. I see a 0 at -1, so that's an asymptote. I see a 0 at 2, so that's an asymptote. What else do you see before we move on?
There's an asymptote.
Yeah, there's an asymptote at x equals 0, isn't there? Okay. There's not a dotted line drawn in for it, but you can tell by the behavior of the graph. This is going up, this is going down, there's an asymptote. So what are we going to have happening at 0, 0? That's going to be a 0 at 0, 0. Okay? So that's kind of step 1. points where y equals 1 or negative 1 stay the same. And again, a lot of this is just kind of an eyeball, you know. Like, okay, so over here, somewhere over here, there's a point that's going to be the same. Somewhere right here, there's a point that's going to be the same. I'm just doing positive 1 right now, I guess. So there's 3 points that are positive 1 that are going to stay the same. I almost forgot my negative ones. So what do we think? Is that parabola? Yeah, it is, isn't it? That's a minimum on that parabola at negative 1, it looks like. And so again, I just put those points on there. My physical reminder that when I graph this, I need to cut through those points. Okay? You ready? Shall we start on the left, or you guys want to start on the right? Okay, if we start on the left, what's happening over here?
It's getting further from the axis, so we can put it closer.
Right? This is going up away from the axis, so we're going to be down here against the axis, right? And then what's going to happen? You're going to aim to cross through this point here, aren't you? And then after you cross through that point, we're going to carefully run up there. That part of my graph was positive, so I was above the x-axis. The next part of my graph is negative. So I'm below the x-axis. What's this look like? Yeah, we're going to flip the parabola, just like in sine, cosine, secant, cosecant. We're going to flip that parabola. And then you touch at that negative 1 point. Now I feel like in between the next two asymptotes, it's almost like connect the dots. Can you see that? What'd you say, Ethan? Yeah. It's a reflected cubic, just because we're going to start high. But yeah, because right here, this graph is positive up here, so we're going to have to start up here. And this is really hard to draw there. I don't really like how I drew that. I feel like it got a little more boxy than it should have, but and then the last piece. Yep. Oh, I can't stand that. Uh-oh, what did I just do? Yep, I forgot. Okay. Oh my gosh. Oh, that asymptote kind of went crooked, didn't it? That's why I'm struggling to draw this so much.
This is an AP arc, so we got
So we're okay? Well, when I'm standing to the side too, it kind of throws my vision off of how I should be lining it up, which is why, so if you see me like I have to be directly in front of it, that's because I'm trying to figure out what it looks like, so. Okay, got all those pieces put together? Really just, it takes thought. I think this last one is probably easier than the first one, figuring it out, but. Okay, do we have time to check homework? We have some.
I believe we